Hi, in this section we are learning on how to test a claim about a standard deviation or variance. The goal here to conduct a formal hypothesis testing of a claim about population standard deviation sigma or the population variance sigma square. Now recall that the sample variance S square is the best point estimate of the population variance sigma square. Now, to conduct a hypothesis testing, we use either the p-value methods or the critical value methods, and we need a chi-square for the standard deviation or variance in this case. And also from chapter 7, we know that all the values of the chi-square are non-negative. So we always go from 0 and to the right, and the distribution is not symmetric. That means it is not a normal shape, and as the number of the degrees of freedom increases, then the chi-square is approaching to the normal z distribution. As you can see from here, if we only have the chi-square with 2 degrees of freedom, then we have the blue curve right here. It is not symmetric at all. Now as I move the number of degrees of freedom to 5, to 10, to 13, 15 and to 30, then we can see that the blue curve, originally the blue curve is not symmetric, but now with 30 degree of freedom, then we are getting to the purple curve, and this one is more symmetric and it is approaching to the normal z distributions. So in this case, the parameter that we are testing is the standard deviation sigma or the variance sigma square. Now we need to use the chi-square. This is the notation chi-square from chapter 7. And there are a few requirements again before we do the testing. Make sure that the sample is simple random sample. And it is normally distributed population. This is a strict requirement. We need a normally distributed population. That means no matter what's the sample size that we have in this case, make sure that the population is normally distributed, and we can do the testing for this requirement using the normal quantile plots from the TI-84 plus in this case, or 83. Now the test statistic is the chi-square, so we use the notation chi-square 0 for the test statistic, and that's equal to the ratio of n minus 1 multiplied by s squared divided by sigma naught squared. S is the sample standard deviation, and sigma square is the claim value of the population variance, and n is the sample size, s square is sample variance, degree of freedom is n minus 1. Okay, so the first part we go with the p-value methods, and then the second one we will go with the critical value methods. Now, as always, we have to determine the null and alternative hypothesis in one of the following 3 cases: two tails, left tail, or the right tail. For the two tails, the null hypothesis is sigma is always equal to sigma naught for all 3 cases. So the null hypothesis is always involving the equality, the equal sign. Sigma equal to sigma naught, sigma equal to sigma naught, sigma equal to sigma naught for the right tail and also the left tail. Sigma naught or sigma 0 is the assumed value of the population standard deviations. And for the two tail, we have the alternative hypothesis that sigma is not equal to sigma naught. For the left tail, sigma is less than sigma naught, and the right tail is bigger than sigma naught. So you can think of this way again. The arrow is pointing to the left, this is the left tail. The arrow here is pointing to the right, so this is the right tail. And the null hypothesis always includes the equal sign. And the next step is to select a level of significant alpha, and this will depend on the seriousness of making a type 1 error. So type 1 error is the probability of getting the type 1 error. The type 1 error is again when you reject the null hypothesis when it is actually true. And the common choice for alpha is usually 0.05. For the p-value methods, we first compute the test statistic, which is chi-square, not the test statistic from here. And for the two-tailed test, it is recommended that the technology be used to find the p-value because it is more complicated. So in this case, in this section, we mostly focus on the left tail and the right tail for the calculation by hands. Now the p-value is just the shaded green area, and we can find those areas here, either here or here. On a TI 83 or 84, or by using the chi-square CDF again. For the student T distribution, we use the T CDF. For the normal Z, we use the normal CDF. For the chi-square, we use the chi-square CDF. CDF represent for the cumulative area to the of that statistic, and or you can use the table A4 to find the area, but please note that the table A4 is based on the cumulative areas from the right of the test point. Now, if the p-value is less than the significant level alpha, we then reject the null hypothesis. If the p-value is bigger than the alpha, we do not reject null hypothesis H0. Okay. And for the critical value methods, we repeat the same process that we did for the last 3 steps, 1 to 3. Now, but for the p-value methods, we instead of finding the p-value methods, we now find the critical value. Now, for the critical values, again, there are 3 cases: left, right, or two tails. We know that alpha is the area to the right of the critical value for the right tail, or to the left for the critical value for the left tail. And then because we have 2 tails in this case, then we must first find alpha over 2. So alpha over 2 is the portion to the right of chi-square of alpha over 2. This is the critical value. And then the other one, this is also alpha over 2, but then we only want to look for this region. So the whole thing here should be 1. So 1 subtract alpha over 2 would give me the area to the right of that. And these are the critical values. And now you can compare the critical value. If the test statistic, the chi-square, the test statistic, is inside the region of the critical regions, then we reject the null hypothesis. If not, we fail to reject the null hypothesis. So let's say that for the 2 tails, if the test statistic turn out to be on the left side of this portion, or the right side of this portion, or bigger than this value, then we reject the null hypothesis. Or it's less than chi-square 1 minus alpha, then we take this value. We reject the null hypothesis. That means it's inside its region, or to the right, which would mean we do also reject the null hypothesis. So depending on the which case here. Example. Let's go over one example to clear everything up now. A can of 7-Up states that the contents of the can are 355 milliliter. A quality control engineer is worried that the filling machine is having some error. So in other words, she wants to make sure that the machine is not under or over filling the cans. So they just want to make sure that the can has 355 milliliter. They don't want to under or over filling the cans. So she just want to make sure that the machine is not over or under filling. Now she randomly selects 9 cans of 7-Up and measures the contents, and she obtains the following data: 1, 2, 3, 4, 5, 6, 7, 8, 9. She also has the information that the population standard deviation was 3.2. Test the claim. Okay, so we are asked to test the claim that the population standard deviation sigma is greater than 3.2 milliliter at the level of significant alpha equal to 0.05. Okay, so we will solve this problem in two ways, using the p-value and the critical value methods. Now, before doing anything, we need to do the requirement checks. This is a symbol, random symbol. Yes, okay, because she randomly selects 9 cans, so this is okay. To check that the population is normally distributed, we use the normal quantile plot to verify that. Now make sure that for the standard deviation or variance, the requirement is very strict. We don't care about the sample size for n. We must check the condition that the population is normally distributed. This is a strict requirement for the chi-square. Otherwise, you get a value that is very different from the one it should be. Okay, so to check that, on the TI-83 or 84, I press the start, choose edit, and I load the data to the list one A1. And then I press the second to start plot, and then I pick the last one, and then I plot the normal quantile plot. And the normal quantile plot does exhibit the straight line, right? The straight line. So we can conclude that the population does have a normally distributed data. Okay, let's try that on here. Step by step so you can see it. Okay, so let's turn on. I now need to load the 9 value inside the A1. So I go to start, edit, enter. I enter all of them to A1. So 351 is the first number. 360, the second one. 358, 356, 359. Next one, 358, 355, 360. Okay, 355, 361, and 352. Make sure 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we store all the data to A1. Now we go to start plot. This is the blue button. So I click second, start plot. I go to +1, enter, and then I need to turn that on first. And then I choose the last one. This is the scatter plot. We don't want that. This is histogram, the box plot. Now this is the one we want. So click enter. The data list is forming A1. It's coming from A1. The data axis is X. So good. So we are plotting the observations against the z-score. So this is the normal quantile plot. So hit zoom. Again, just exit out, hit the zoom, and choose the zoom start, which is option 9. Hit enter. And yes, this is the one that we got down here. Right, okay. And this is a straight line. It's close to a straight line, so that's good enough. Okay, so the next step is we need to find the sample standard deviation sigma. Okay, this is a typo. It should be the S. Sample standard deviation is the S, not sigma. Sigma is the population standard deviation. So this is the S. It should be the S right here in this formula. The S. S is the sample standard deviations. So we need to find that. Now we are given 9 data points. We can do that easily on the TI-83 or 84. Now you go ahead, press the start and go to calculate and pick one variance start, and then enter the list of L1 and click calculate to get the statistic here. And the X means this is the sample standard deviation S. So make sure you know that this is the typo, not the sigma. It should be the S. Okay, so I just show you here to get the statistic of this figure here. All I do now is I go to start. I move to calculate, right arrow, and I pick one variance start. And I know that the data I want to find the sample standard deviation was the L1. We store the data to L1. So hit enter, calculate again, hit enter, and it should give you the S, which is the sample standard deviation S, is 3.464. Okay, so you have everything now. This is the test statistic. You have N, the number of data points, which is 9 data points. S is the sample standard deviations. Sigma naught, this is the sum, population standard deviations, and we also got that info from here. Population standard deviation was 3.2, right? So now we are testing the claim that sigma is greater than 3.2, bigger than 3.2. So you have two cases: sigma bigger than sigma naught, which is sigma bigger than 3.2. And because this one does not involve an equal sign, that means this becomes the alternative hypothesis. And therefore, sigma equal to 3.2 is the null hypothesis. So we are testing the claim of sigma is bigger than 3.2, which is the original claim that the problem wants us to do. Sigma is greater than 3.2, test the claim. So we are testing for this claim, and we know that sigma equal 3.2 should be the null hypothesis. And because this is the right arrow pointing to the right, it should be the right tail test in this case. We know that N equal 9, 9 sample points. Alpha is 0.05, the level of significance. We are given this. The sample standard deviation S, we got that from here, 3.464, and the sigma naught is the one that from here, like 3.2. The given value is given to us, the claim value, 3.2. It's right here. Population standard deviation was 3.2. So we assume that we got that. The test statistic is right here. Sigma chi-square naught square equal n minus 1 s square over sigma naught square, and we just take all the value we got here. 9 minus 1 s is right here, square, sigma naught, which is 3.2 square, and everything gives me 9.374. Now just briefly draw the curve. It is not symmetric, and we know that the test statistic gives me 9.374. You want the area to the right of 9.374, and that should be the value of the test statistic. The value of the p-value. And the p-value in fact is just the chi-square is bigger than 9.374, the area to the right of 9.374. Now if I use the table A4 to find the area to the right, we know that we need the degree of freedom is 8, because 9 subtract 1 and subtract 1, which is 8. 9 subtract 1 is 8. And then we can see that we need the test statistic to be 9.374, but then from here, this is the area. this number here on the first row here. This is the area to the right of the critical value, right? This is the area to the right, and the value inside here is the test statistic. So we look for the value of 9.374 on this row because we have 8 degree of freedom. So we look for 9.374, and we are matching that here to find the area to the right because we are looking for that. And you can clearly see I cannot find 9.374 from this row. So 1, 2, 3 something, there's no 9.374, and clearly the table A4 is very limited to have the value of the chi-square to be 9.374 at the degree of freedom 8, and therefore we cannot get the value from table A4, in this case for the p-value. And we need to apply the TI-83 or 84 to find this area. And we have to use the chi-square CDF, right? So the commands for the syntax is as follows. The chi-square CDF, this is the cumulative area from the test statistic. Okay, so we use the lower bound. The command for that is the lower bound, the upper bound, lower bound comma, upper bound comma, and the degree of freedom. Okay, the lower bound is 9.374 because we start from here. The upper bound we go all the way to the right, very far to the right, so I put that 10 to the 99 power. And then the degree of freedom should be 8. So on the TI-84 plus we can enter directly. It's very convenient for TI-84. They give you okay, let's go back here. So on the TI-83 you have to know the syntax to know that, okay, you must type the lower bound first, comma, upper bound, and then the number of degree of freedom. But for the TI-84 plus, it's very convenient. You don't have to know that. Just go to this distribution here, second distribution. Okay, go back all the way. So second distribution. And we look for chi-square CDF, which is, I believe, the 8th option here. So they display the what they ask you for the function. So you don't have to know the syntax for the TI-84 plus. It's very good for this type of problem. So the lower one, I enter the test statistic from that point, 9.374. The upper one, I just want is going all the way to the right, forever to the right. So I put 10 to the 99, some huge number. 10 to the 99. And then the degree of freedom, DF is degree of freedom, I know that's 8. And I paste this one into the syntax, which is right here. They automatically paste everything that you just enter into a correct syntax for the chi-square CDF function. If you're using the TI-84, then you have to know that the first box should be the lower bounds, comma, the upper bounds, comma, the degree of freedom. You have to know the syntax because they don't display this window here for you using the TI-83. But for TI-84 and the one that's after that, they already have the improvement that it's showing you the display. They display the function and asking you what to input, and then hit the enter key, and it should give you 0.311. And this should be the p-value to the right of that statistic. And because 0.312 is bigger than the alpha, which is 0.01, then we do not reject the null hypothesis. We only reject the null hypothesis if the p-value is less than the significant level. Okay, so that was the p-value method. Now let's try the critical value method. Now for the critical value methods, we know that this is the right tail, so I need to find the critical value instead of the p-value. The alpha is 0.05. Now I need to find the critical value in this case. And how do I do that? I know that I was given the area to the right of that is 0.05. So using the table A4 is 0.05, and we know that that is 8 degree freedom, 0.05 with 8 degree freedom. Then I can find 15.507 is the critical value. Okay, so the critical value here is 15.507 from the area to the right alpha is 0.05 and 8 degree freedom. And we know that the test statistic is 9.374 is below 15.507, or it is not inside the critical region. Therefore, we do not reject the null hypothesis. We only reject if the test statistic is inside the critical region. But now it's turned out that 9.374 is less than 15.507. We do not reject. And again, we are reaching the same conclusion using both ways. So the critical value and the p-value, they are similar in the sense that they always give you the same results from either ways. And you can see here, without the technology, it is better than to use the critical value methods for testing the hypothesis about a population standard deviation or variance. So in this section, it is more convenient to use the critical value method instead of the p-value, because the table A4 can give you all the value that you need to find a critical value, but not the p-value. So in this section, the last one, testing a claim about a standard deviation or variance, I recommend that we use the critical value methods, because the table A4 is already available to you if you don't have the tier 84 or 83. And now we can make conclusion, because we do not reject the null hypothesis. So we do not reject that. So go back to the null hypothesis right here. It is right here. We do not reject this one. That means we cannot be for sure to conclude that the standard deviation is greater than 3.2, right? Because we do not reject the null hypothesis. That means there is insufficient evidence at this level of alpha to conclude that the standard deviation of the can contains 7 ups is greater than 3.2 milliliter. Because we do not reject this guy here, that means we do not have enough evidence to say that the null hypothesis is true, or to test the claim that it should be bigger than 3.2. We cannot say that. Okay, so that's how you do the testing for a population standard deviation or variance. In this case, is the standard deviations. And thanks for watching.